Everybody, welcome to our presentation this morning. My name is Paul Reid and I'm the CEO of Mimomax Wireless. Today we're going to talk about some smart radio network design, so thanks for joining us. Presenting with me today I have two of our senior team, our engineering team. So we've got Doug McConnell, so I'll ask Doug to introduce himself. Doug's our CTO, and we also have John Wilkinson, who's our network coverage design manager. So to start with Doug, and just ask Doug to introduce himself, and before we sort of get into it.
Yes, hi, I'm the CTO of Mimomax. I've been involved with Mimomax since the inception, and prior to that I was in various engineering management roles within Tate Electronics for many years. I've been in the industry for over 40 years.
And John, if you wouldn't mind.
Good morning, everybody. John Wilkinson here. I'm the network design manager. Like Doug, I came from Tate Electronics, and I was worked for them for about 20 years. I've been with Mimomax for about 7 or 8 years now. Focusing mainly on network design, path planning, and the likes, and have some experience outside the Tate group as well, in heavy electrical and also the rail industry. Thank you.
Great, thanks, John. So, John and Doug, can you see my screen okay?
Yes.
Yep, great. So, just going to kick off and get into the presentation this morning. So, I think we've got a good number have joined this morning, and I noticed that a few are still joining. So, but I think, given time-wise, we'll get straight into it. So I've introduced the panelists sort of today, and the topic is going to be smart radio network design. So Mimomax have done a number of smart radio network designs now. So in fact, some of the largest field area networks in the US have been undertaken by Mimomax. So the team have built up a lot of experience and know-how, and today we're really just going to share that with you, and later on during the course of the presentation we'll open up a panel discussion and finally finish off with a Q&A session. So sit back, enjoy, and please feel free to think up questions and submit them through the course of the presentation, and we will we'll get to them at the end. So just a quick introduction to Mimomax. So Mimomax was founded in 2007, so we've been around now for a number of years, and we're headquartered out of Christchurch, New Zealand. That's where the team are sort of situated this morning. We've got an early start here in Christchurch, and that's where the main or headquartered office is situated. We have regional offices in Phoenix, Arizona, and in Portland. And our key focus is utilities, public safety, transport, mining, oil and gas. Our solutions really revolve around multi-tier field area networks, and the guys will talk about what multi-tier means to our technology, and SCADA network for utilities. And the whole premise is what we do is mission critical, ultra reliable, backhaul and licensed private narrowband channels. So without further ado, and Doug, I'm happy to push through the slides for you if that works for you. But without further ado, I'm just going to ask Doug to jump in and just talk on initially choosing the right antenna. Thanks, Doug.
Yep, okay. So we start off with just the question, why use Mimo? Well, the main reason for using Mimo is the doubling of capacity that we get through our 2x2 Mimo. So we get twice the capacity that you would on a equivalent CISO system. There's another advantage that comes with that, is that in order to decode the Mimo signals, we use some fairly advanced equalizer techniques to unscramble the Mimo components. This has a side benefit of largely mitigating a lot of the multipath which would otherwise deteriorate the performance of the signal. So it's an additional benefit that comes with our advanced equalizer in the Mimo. As far as propagation of Mimo, it's interesting. Often it's associated with a bit of a concern that it requires special antennas, that it has a lot of other characteristics that make it difficult and special. It's not really the case. You can use pretty well any normal antennas, although for convenience, it's usual to use a dual polarized antenna. It means there's only one antenna to mount. And in the case of in the case of panel antennas, in essence, they're no more complex. They simply have an additional feed point on the patch. Apart from that, they're very much the same. In the case of Yagi antennas, they basically have both horizontal and vertical elements. Now, obviously, when choosing the antenna, you need to choose the antenna with a view to meeting the various constraints and performance requirements. From one point of view, there's the environmental perspective. Is it exposed to snow and ice? Are you concerned about the visual impact? And of course, from a performance point of view, there's considerations of the beam width, the front to back ratio, the existence of side lobes, which potentially offer an opportunity for interference coming in from different directions. Note, whether or not it's two separate antennas or a dual polarized antennas, probably the single most important requirement is that there's a good amount of isolation between the polarizations, preferably greater than 20 dB. As I've said, snow and ice environments, that tends to point towards using a panel antenna, which tend to be more tolerant of that. Obviously, you can use a Yagi with a protective radome, although that does increase the wind loading. If you're wanting to minimize wind loading on a tower, sometimes Yagis are more attractive because of the lower cross-sectional area there. The front to back ratio and the side lobes are typically better with a panel antenna, and I'll show an example of a couple of actual plots of the radiation patterns just to reflect that. Here's just two examples of antennas that we use. On the left is it's actually a radomed Yagi, 12 dBi. On the right is a compact panel antenna, also 12 dBi. Same forward gain, but the pattern is a lot cleaner on the panel. So in order to get coverage across a field area network, repeated frequency reuse is required. And to do this, you need sufficient channels so that you can manage the co-channel interference. Now, there's no hard and fast rule about exactly how many channels you need, but what we find is that particularly in varying terrain, you need a reasonable number of channels. We've found in practice about 14 channels is ideal. And obviously, in the case of the 700 megs upper A block, this limits the practical maximum channel size to 50 kilohertz, so that you've got room to fit in the 14 channels. Another issue is that often with because of difficulty in getting into various areas of terrain, you need high sites to cover particularly sparsely populated areas with difficult to access endpoints. The problem, of course, is that once you put a user channel on a high site, you tend to limit the ability to reuse that channel within the network. And so again, that sort of says have some spare channels up your sleeve in your channel plan to enable you to do that without causing interference across the network. And of course, the other thing that crops up is that your system will often butt up against other people in adjacent regions, adjacent geographical areas, using the same frequency band. Having some spare channels gives you the opportunity to rearrange the channel plans to avoid conflicts at the boundary. If you don't have any spare channels, you can often end up in a bit of a tangle. Obviously, all parties need to be good citizens. You need to ensure that you're aware of adjacent users and consider the interference caused by them to your system and by you to their system. So with our system, we can offer 50 kilohertz, 25 kilohertz, or even 12.5 kilohertz if required. In terms of systems that are deployed in the US, we have both 50 and 25 kilohertz systems. I don't think we've got any 12.5 kilohertz ones actually deployed. We assign the channels in such a way that we have, for 50 kilohertz channels, we'd have 20 channels, but we leave one channel at the top and bottom of the band as guard bands, just to provide a bit of additional protection for adjacent services. Thank you.
Thanks, Doug. I'm just going to move on now and invite John to speak and have John speak on radio network design. So, John, I'm happy to continue driving the PowerPoint if that suits you, or happy for you to take.
Yeah, I've got it up here as well, Paul. And
okay.
yeah, okay. So I'm going to be talking about radio network design. Hang on, you've handed it over to me, Paul, so I'll grab it anyway.
Okay.
Is that coming up? Is it coming through, Paul?
Yep.
Yes, you are, but you're not in the full screen presenter.
Yep. Just go now. Thank you. Okay. So I'm going to be talking about radio network design and the tools that we use and the processes we go through, and just to give you a feel for what is out there and what is available to carry out radio network design. RF predictions, they're very much that. They are prediction. They're not an exact science, and it's really impossible to precisely model the real world, and we need to keep that in mind. And so therefore desktop modeling it's not a replacement for field work and good industry knowledge. Getting out in the field, having a look at the sites, ascertaining what the potential issues are, things like, you know, if you're hard up against buildings or you have a tree that's growing over the endpoint outstation, that's not going to be represented in the modelling. You know, I must stress the importance of site surveys and path surveys, both from a physical and an RF point of view, again, as we said, to ensure that the site is physically okay to be implemented, and then the RF side of it to look at interference and issues while coexisting with other equipment on the site or interference from outside the site. There's a lot of good modern 3D visualization tools available now, especially Google Earth, which is essentially freeware. We use that all the time, and it's invaluable for the network planning side of it, and also for sharing results with customers. There's a wide range of network design tools available, everything from freeware through to quite sophisticated, expensive tools, and the sort of work that utilities would be undertaking. You know, it's your upfront investment just for, say, EDX or Cellplan could be in the order of 20,000 plus your ongoing maintenance, and then there's always the cost of training people up in the use of the tools. GIS data sets can be a considerable cost, especially if you want to go to a high resolution database. Initially, I'd suggest you consider the data your organisation has access to, including free sources. In the US, that'll be USGS, and then look at the commercial data for your detailed design stage. And as I said before, you know, you need to take into consideration the costs of the tool operation and training people up to use the tools. There's a big learning curve, even with the free tools that we'll discuss. It takes some time for people to become proficient in them. Going on to the design tools themselves, something we've used for a long time, and a lot of people in the radio industry do, is Radio Mobile. It's a good introduction to radio network planning. It's essentially a donationware tool, and in the right hands you can get professional results. It's excellent for a first cut, what if, whether it's a point-to-point path or a wide area coverage, say a point to multi-point system, and it's easy to set up a project. And you know, if you've got the data in front of you, as far as the sites, it's, you know, for a path you could look at that within, say, 10 minutes, especially with the integration with Google Earth. It can be configured to auto download terrain and clutter files, which is the beauty of the tool. A lot of the professional commercial tools, they have their own proprietary data set formats, and you need to prepare the data sets or have a significant on-site database with all that data ready to use, whereas Radio Mobile can be used anywhere you've got an internet connection. It integrates well with Google Earth, both from an import and export point of view, and we'll see a few examples of that later on. You can utilize your own in-house terrain and clutter data. We've developed our own data sets within Mimomax. There's no, as far as how it compares to the commercial advanced tools like auto site selection, frequency planning, and path availability calculations. As far as availability calculations for point-to-point, you can always take your calculated fade margin outside that and run a spreadsheet to calculate the availability to one of the standards. It's either the US standard or ITU. As I said, it's essentially a donationware tool, very cost effective from that point of view, and there's a very, very good user community in behind that. Path loss is an industry standard when it comes to point-to-point path planning for, you know, VHF, UHF radio, microwave. Most organisations have utilised this or are aware of it. It's cost effective relative to other commercial tools, for example, EDX or Cellplan. In our case, you can manually add clutter from local knowledge or Google Earth observations. We find that very useful, especially the Google Earth side. Actually being able to virtually travel the path and look at the obstacles or clutter land cover there in the path. And in Google Earth nowadays, there's quite a lot of 3D, you know, good information in the 3D building layer as well. Has ray tracing capability, which is good for identifying potential multipath and ducting issues. And you can also model the impact of tidal heights and K-factor variation. So if you've got an oversea or overwater path, you can look at the impact of the changes in the water height, especially in tidal paths, which can be, you know, some meters, and whether that's, you know, you're going to be able to sustain your link during those changes. Limitations from a point to multi-point or wide area coverage capability, it's not great. Radio Mobile is actually a much better tool to use for that. There's no online server map or map server capability. You need to set up the maps or generate them. and reference them into the tool before you can get started on a project. And it doesn't integrate well with Google Earth. I think it can export a line on the ground as far as the path is concerned, but you know, radio mobile is much better at that. EDX, Signal and Signal Pro, from the point of view of the Tate Group, which Mimomax is part of, we come under the Tate Trust. We've utilised that tool for 20 plus years. We used it initially for 700 MHz FAN designs before moving over to Cellplan. It works well, very well from a technical and mathematical point of view. It supports many technologies. It has its own proprietary database formats and conversion. They provide conversion tools for that, but you know, there's a reasonable amount of pain in converting that data. It takes a lot to get your head around the process. And the cellular network design capability isn't as strong as Cellplan, and that is one of the reasons we moved to Cellplan. Our tool of choice at the moment for detailed network design for the fan area networks is Cellplan, and for us it's a one-stop shop. They have a complete drive test solution plus very powerful network design tools. And you know, the Cellplaner is the main tool that we use for the network design with cell performance for vast analysis such as site selection and frequency planning. They have their own in-house capability to develop GIS data sets, for example, 5 meter data sets. We also develop our own data sets in-house in Mimomax, especially for the early stages of a project. They have very good support, very proactive. If we ever had problems, they generally sort it out within a day or two, and that's hard to come by from some of the other vendors. I mean, the tools are available on an annual perpetual licensing basis plus a support contract, and the cost is comparable to EDX. Like any of these tools, advanced tools, there's a very high learning curve, but again, the training is we've found has been excellent. Google Earth, I'm not too sure what we would do without Google Earth nowadays, and we just use it all the time, especially in conjunction with the tools that I've been talking about. And it just enables you to visualize the output from the tools, whether it's a point-to-point path or a wide area coverage plot with all the assets, and to virtually tour the results, and especially now in some of the cities, and for example in the US, the 3D building layer is very accurate. I think you can see an example there on the left, bottom left. There's a point to multi-point application that has been deployed, and you can see the 3D building layer there is up, and then enables you to look for obstructions, and even down to the individual trees modeled. You can actually do a virtual site survey without leaving the office, although I would recommend you still do an on-site survey as well. It's important to, when taking results, especially the point-to-point path results modeling from your tools through to Google Earth, to actually make sure you calibrate the ground heights that are presented within Google Earth, because they can vary from your database within your design tool, and that can change with the 3D building layer on or off. I've seen examples where the heights within Google Earth have changed upwards of 5 to even 10 meters, although that seems to be getting better. So the ability to export into Google Earth is something that is improving with from the vendors. Some have been slow to pick that up. I mean, with Radio Mobile, I worked with Roger probably 16 years ago to implement the path exports you can see there in the bottom left, and we've also worked with Cellplan to implement a similar feature, and that's worked well. Wide area coverage plots present well in Google Earth, and again, as I said, enables you to do a virtual exploration of the coverage. The the ability to add custom icons and fixed legends, and bundle up a professional package that you can send to your team or management or customer is excellent, because at the other end, they only require Google Earth and basic knowledge to actually drive it. From a GIS dataset point of view, we use GlobalMapper. It's really the Swiss Army knife of GIS. It's able to open most industry standard GIS formats. It's very cost effective and easy to grasp relative to ArcGIS and MapInfo, or even some of the open source GIS tools. It's ideal for creating terrain, land cover and building layers. It has a batch and scripting capability. And you can do things like integrate terrain layers. So if you've got a mining application where you've got a very detailed model of the mine pit, you can essentially punch that into an existing terrain database, whether it's SRTM1 or 2 or a higher resolution database, and generate a final terrain layer that can be used within your modeling tool. As far as the GIS databases themselves are concerned, it's big data. It's nothing to have 10, 20, even 30 gigs of data for a project. Beware of BRF versus surface models. Understand what you're actually using. For example, the SRTM data, which is getting quite long on the tooth now, didn't always discern well between forest and building covers. So your clutter heights or land cover heights can actually be built into your terrain model. As far as sources of the GIS data, there's free through to expensive higher resolution. So some of the cellular telcos will think nothing of spending hundreds of thousands on their data sets. But then again, there's very good free data, for example, in the US from the USGS. So it pays to look at what is available freely and what you can actually generate or convert yourself first before spending a lot on commercial data sets. As far as terrain resolution, what is required, the accuracy there or resolution is 40 to 50 lambda. The wavelength is adequate. So for 700 megs, it's about 15 meter resolution. From the USGS now, they have for the whole of the US, there's your 1/3 arc second 10 meter bare earth data is available. A lot of that now is based on LiDAR scans, so it's inherently got a much higher resolution than 10 meters, and you can see that in the latest tiles. And a good part of the US now is covered by 1 meters, although when you start getting down to 1 meters, the data sets are getting very big to manage. Map overlays for presentation. OpenStreet road vectors are very good. They're continually being updated. You also got your Tiger data sets in the US. And the Google Map and Bing map layers are actually way better than some of the commercial imagery you can buy, especially on the fly and being up to date. Clutter land cover, that's a separate layer on top of your terrain. As I said before, beware of terrain or encompassing the clutter heights. As far as what's available there, we use in-house through to commercial high resolution data. And on the right there, I've got a couple of examples. One's a database we've generated ourselves, which is taking the latest 2016 NLCD data from the land cover data from the USGS and overlaying that with the OSM roads. And that's a project in the US, which gives a reasonably good result. We sample that down to 5 meters so we can actually capture the roads. And below that is an example of 5 meter commercial data, which you start to pick up the buildings and whatnot. So a lot of our customers will go to the 5 meter, for example, for the final network design or detailed network design. Antenna patterns, there's many different pattern formats out there and standards. The vendors' conversion tools don't always work properly. Every time someone asks me for an antenna pattern, I'll roll my eyes because I know there's a reasonable amount of work involved in converting them and making sure it's done properly. So it always pays to check the patterns are supplied, and also after you've done the conversion, because as I said, the tools don't always work. Quite often you end up going back to a text notepad approach or Excel, and the conversions can get quite complex. It's also, it's important to consider, the ideal free space model of an antenna versus as installed pattern, and they're usually not the same, especially for the likes of an omni antenna put on the side of a tower. You're going to get shadowing or distortion, and it is important to model that. It will have a significant impact on the as installed pattern. And also we get involved in modeling of phased antennas, especially in the overlap regions, ensuring that you don't have phasing nulls and that they are mounted as best possible to optimize the finished result. Design of a 700 megs fan. This is a process we've gone through with the customer, and just to give you an idea of the steps, especially in the early stages of the project through to the detailed design. Quite often we'll run a preliminary concept design on radio mobile because it's quick and efficient, for to get a feel for the network design, the scale of the design, and without excessive time and cost outlay. And for example, the cost outlay could be involved in preparing data sets, GIS data sets. Even if you prepare them in-house, there's still a reasonable amount of time involved in that, or procuring those externally. The next phase of the network, of a network design we've done, we developed that in EDX Pro. Again, was based on in-house developed terrain and clutter data. And we've also, after that, conducted drive testing here in New Zealand to get an initial feel for the propagation characteristics of that and use that for calibration within EDX. The pilot system was then installed with the customer, where we had 4 3-sector sites, plus a tier 2 layer with 2 of those sites being deployed. We did in-country drive testing in the US, and we carried that out on all of the pilot base stations deployed, and we used that then to calibrate the tier 1 and tier 2 propagation models. So that's in country on the frequencies that are being utilized, and we get a much higher accuracy in the model calibration. About that time, we shifted over to our new tool of choice, which is Cellplan, and we carried out the detailed network design in Cellplan, and the project is still supported in Cellplan. Drive testing, this is something we have quite a bit of experience with. Why do you drive test? One is to calibrate the propagation models, and the other is to verify the network coverage after it's been deployed. As far as the drive test vehicle setup, we have the sampling antenna. It's very important to use an antenna with a known pattern that is suitable for the task at hand. So it has a good omnidirectional response and a good vertical response as well, because as you drive around, the vertical angle to your base stations is going to change. Also it's essential to utilize good type bandpass filtering to block out any high carriers that could upset the sampling receiver. For the drive testing, we've utilized our Mimomax radios, or if we're doing only a small number of carriers, or we utilize the Cellplan cell spectrum analyzer, which is can handle a large number of carriers. We've done in the order of, say, 10 carriers at once. And traditionally in the past, you would have had to have 10 receivers, and with the ability to pull all that off one receiver, software-defined receiver, saves a lot of RF plumbing, so to speak. Of course, you have your GPS, externally mounted GPS, and you know the accuracy of those is better now, and also the sampling rate, and the laptop for the data collection. It's a big data exercise, both from a collection point of view and post-processing. It's essential to check and sweep all the RF components at the end and the start and end of each day. You know, there's nothing worse than, say, having gone through a whole day's or a couple of days of drive testing and find that something was wrong. So there's no time or room for errors. It's a very time-consuming activity, and essential to back up that precious data daily. Hard drives do fail, and I've spoken to people who've had that happen and lost a few days of drive test data. As far as, you know, as well as the actual network design as well, process as well, we get involved with, you know, for example, tower mapping, where we're looking at the exact location of all the antennas on the towers, and along with their RF details, what are the services operating on those antennas, and we utilize that for determining, you know, the aperture for new antennas, and also detailed interference analysis, looking at the possibility of blocking carrying due to high level carriers from other services on the site. Of course, our, you know, if we're implementing a radio system outside, to look at it from the other point of view, us interfering with the existing users, and also the isolation between the antennas. So as well as the carriers, also noise floor and adjacent channel sidebands coming off or sidebands coming off the carriers, and elevating the noise floor in our receiver operating channel. So it's important to go through that detailed design. That's something we get involved in. And as far as interference and noise analysis, it's best to look at the interference up front. It avoids costly surprises after the system's been designed and installed. And, you know, it may be a situation where a site is unusable due to whatever reasons, higher interference, or you know, the existing equipment there isn't facilitating the use of your system there, and there would be nothing worse than implementing a system at great cost, running all your feeders, antennas, doing the full installation, to find out that you've got unusable interference. So we need to look at the equipment specifications. We go back to the tower antenna mapping. We look at the impact of the carriers on selectivity. We'll run an intermodulation analysis, and we'll also quite often do site noise measurements to analyze the impact on the effective receiver sensitivity. So you can then, you know, most sites will have some elevated noise floor, some worse than others, and you can take that those measurements and then implement them into the design tool and look at the impact on coverage. Here's a case study where we've utilised design tools, Google Earth, and we actually predicted this problem, and it was a problem in the end, and we were able to deal with it. So what we've taken there is from Radio Mobile, we've taken the point-to-point path model into Google Earth. We've calibrated the ground heights correctly with the 3D building layer on. As I said before, the ground heights can change. And this particular installation was not reliable. We were having multi-path fading issues. And as you can see there, you can see the red line there, which is the second Fresnel zone, is essentially grazing the top of the solar panels, which actually on a nice angle which even enhanced that. A lot of people think, well, I'm not getting good signal, it's not working well, I need more height. In this case, it's sort of counterintuitive. We dropped the antenna height down to essentially smother the second Fresnel zone. So in that case, there's 2 freeware tools or or donationware for Radio Mobile and Google Earth. We were able to pinpoint that problem remotely and advise the customer on what to do. So just an example of what the modern tools can provision or help you with. And that's everything from me. Thank you.
Thanks, John. I'm just going to ask the panel to turn on their video, and we're just going to jump into that panel session now. So hopefully I'm sharing. I can see Doug on and John on. Well, thanks, Doug and John, for that that talk. That was fantastic. We had a question come through, and I want to just address that now. So for clarity, and one of the confusing things that I've found is that we talk about tier 1 and tier 2 within Mimomax, and that's sometimes it's in conflict with the tiers of networks in terms of transport systems. So the highest tier of transport, which might be fiber or microwave in industry, is sometimes called tier 1. And then you move back from there to the radio network and other aspects in various tiers. So in Mimomax, what we have done is we've developed 2 tiers of technology that coexist within the same network. So tier 1 is our high capacity, low latency radio technology. But then we have a narrow or an IoT technology, which is a second tier, which is higher latency, lower capacity, but at a lower price point. And what that does, it balances out the need to have some endpoint connections which are much more mission critical than others, and they require much more capacity and lower latency, and balances that out with the sheer number of endpoints that need to be able to support connectivity and scalability. So that's where we start to talk about tier 1 and tier 2 within the Mimomax network. So just going to jump into the panel discussion, and we've got sort of 10 minutes, but we have got a lot of questions come in, so I want to also make sure we've got time for that as well. So the first thing I just want to discuss with the panel, and something that comes up for me all the time, is when we get into a network design and it's a large field area network, the question arises around availability. So, what is the availability requirement for a large field area network that we typically come across? And often this can be confused with availability of point-to-point networks, which are much more rigorous in their requirements. So, John, maybe I'll kick off with you on the availability discussion, and just what is it that typically we would look for in a field area network, and how would we sort of drive the design around that?
Thank you, Paul. Yes, as you mentioned, a lot of people are familiar with, say mission critical point-to-point path planning, where they'll be designing availability for 5 nines, and that would be either to the Vigance method, say for the US, or the ITU standards. And as an example, you're going to need, it depends on a number of factors. One is the frequency, the path length, the inclination of the path, the terrain, whether it's smooth or rugged terrain, and the area of the world. The availability calculations take those parameters into account. And so if you're looking for 5 nines, sometimes you can end up around 20 or 30 dB fade margin for a point-to-point mission critical path. For point to multi-point, for say utilities, we're typically designed to 99.9% availability. And with the types of paths and the links that we're looking at, 5 dB is typically enough to provision your 99.9% availability. As on top of that, that would be from a point-to-point point of view. We need to make sure that we're also taking into account any interference or anything as well that would be, say, slightly elevated noise floor that may be reducing the receiver sensitivity. But on top of that, about 5 dB is enough for 99.9%. As far as wide area planning is concerned, we would normally provision, say, another 5 dB. So you're looking at, say, 99% area coverage. So typically we'd be looking at about 10 dB for wide area network planning. So you're doing your coverage plots.
Great, thanks, John. And so what I'm hearing you say there is, we might end up with a point-to-point link, and typically we might design that for 5 nines. However, when we come to large field area networks, it's more realistic to sort of head towards 3 nines. And
that's typically what people are asking us for too. And okay. Sort of your SCADA data collection. I mean, if it was a a protection link or something like that, we'd take a different view to that, especially for the electrical utilities. We're mostly designing to 10 to the minus 7 bit error rate as well. So it's a wee bit more than what our competitors will be using.
Yeah. And Doug, do you have anything to sort of add to the rationale around, 3 nines in a large field area network?
No, I think John's covered it pretty well. I don't think there's much more to add to that.
Okay, thanks for that. I guess the other thing that that we come across quite often is the trade-off between our style of design, which is kind of morphed towards a much more cellular sectored style of design. And there's a couple of reasons we do that, as opposed to simply, driving towards an omnidirectional type, antenna, and then, looking for a lot of area coverage or the like. So, Doug, rationale for Mimomax in terms of driving towards that sector design over and above perhaps, simply installing an Omni.
So, okay, in terms of the base stations, obviously going to a sectored base station gives you 2 benefits. Firstly, there's the capacity increase associated with the fact that you've now got 3 separate paths, if you like, or groups of users. But also you get the gain benefit of the antennas. When you look at the remote stations, one of the things that we've investigated quite a lot is moving to directional antennas there. Now, it's pretty obvious that you're going to do that because you're pointing at a base station. But what we found and have done quite a bit of investigation into is that it changes the rules for your frequency reuse in a very beneficial way. Most of the frequency reuse study that's gone on has been directed at cellular networks where obviously the terminals have omnidirectional antennas and you can't make any use of that. It turns out that by utilizing the directivity at the remote ends, you can substantially increase the protection that you get for reuse, and in fact it changes the sort of tessellating patterns that you use to some extent, and so that gives us a significant advantage. It's complicated by the fact that, of course, terrain trumps everything. You can have this nice frequency plan that says, yes, I'll reuse with a given radius, protection radius, so how far that you assume that you're not going to get any interference from. But of course, when you look at the real world, and particularly with variable terrain, you'll get signals propagating right across a valley much better than they propagate to the nearby neighborhood sometimes. So the general goal of planning for frequency reuse is helped by using directivity at both the sectored base stations and the remote ends. But at the end of the day, you need to run your modelling tools to work out what actual coverage and potential interference you're going to get from any given plan. And that's why I come back to the answer of saying you needed a reasonable number of channels, because yes, you can design a system with sort of, you know, a 7-channel reuse or some lower reuse there, but in practice, when you put it in a complicated environment where you've got high spots and difficult to access areas together, you tend to need more channels than you think. As is usually the case with utilities, most of your substations and things aren't put on you know, nice, clearly accessible places. They're often in gullies or valleys, you know, so the propagation conditions aren't ideal.
So Doug, I'm just going to ask a question because I know I've seen plenty of these come out of your office, and these are tessellation patterns for reuse and the theory behind that. So I've seen coming from you in the past, you know, a number of those tessellations, and looking to kind of drive towards the, I guess, the theoretical view of an optimum reuse pattern. So just want to ask you about that before I go over to John, and then just ask, well, what are the practicalities of actually realizing that type of pattern in an actual design? So initially, you know, from the theoretical point of view, Doug, what is your view with respect to the reuse patterns?
Well, if you started with a very simplistic situation where you had sort of, you know, reasonably level ground with constant clutter on it, of course, what you end up with is this nice set of hexagons that you always see in the sort of cellular pictures, and they're reasonably regular in size, and you cover your area with a bunch of hexagons butted up against each other. What the antenna directivity at the remote does to that, you still end up with the same basic pattern, but the pattern in which you reuse the frequency changes. So rather than just considering a sort of one hexagon surrounded by 6 others, which will give you a sort of a 7 times 7-channel reuse pattern, the directivity actually allows you to get more reuse than that over the system. However, as I say, that's all based on this rather idealistic view with sort of flat ground and constant clutter. So, you know, but we certainly can increase the reuse over using omni antennas.
Great, thanks. And just John, on the practicalities, so, you know, Doug's talking about a flat Earth model and a theoretical reuse pattern that might be optimum, but the practicalities of actually, and I know you've done plenty of these designs, you know, how do you go about the practicalities of designing a reuse pattern?
Yeah, as we said, there's quite a difference between you know, an ideal situation and what we're actually coming across in the real world, and it depends on the project as well. So we've done some projects that are constrained to you know, maybe a small area, a large city, through to statewide deployments, and you know, we have different numbers of channels assigned to those projects. So and also, you know, it's not these sites are not evenly spaced. They are what they are as far as utility, what they have available, their substations, existing infrastructure, and that doesn't, or you know, never lines up with the perfect, you know, cellular planning scenario, and the elevations across a project can change, even though we may think it's a relatively flat area. You know, when you go from one side to, you know, a city and start moving across, you may find there's 1,000 feet deviation, you know, or change in elevation, and therefore again, as you were saying, it's not a flat, perfect world, and the reuse it does throw some challenges in there for the reuse. We're also nowadays, we're not running low bit SCADA rates at 9.6. We're running high order modulations, and the C to wire requirements are higher, and that puts pressure on the frequency planning as well. So essentially, what we're doing is we will take the candidate sites from the customer, and there's normally a lot more than what we require, and we'll build up the project, and then we'll do an auto site selection. There may be some pre-selected or locked-in sites from that may have been pilot sites or just key sites that the customer wants to use. And we'll do a site selection, we'll look at the coverage we achieve from that without frequency planning, and then we'll do the frequency planning. So quite often we'll do quite a range of a number of channels, and let's say from maybe 10 through to 18, and then we'll look at the results from that and look at what we're achieving and what is the best number of channels to be assigned to the project based on that. Also, some customers are designing for very much for a wide area approach. They want to be able to deploy an endpoint anywhere within their project fan polygon area. Some customers have very much dedicated outstations that are existing, and we can focus the design on those outstations, and that does change things. It's less constraint on the frequency planning. So, in that case, I know one customer we've got about 10 channels, with another customer, who's got a not so difficult terrain, but the terrain is changing. We may be using around 14 channels, plus some on high sites, give that umbrella effect to pick up the difficult sites or the sites that are out of the main primary city area, for example. So you may get upwards of 16, channels assigned. So
thanks, John.
That's a bit of a summary, but yeah, there's no
that's
golden rule there.
fine. Yep, no, that's great. That's great insight and quite practical. I think we've got about 3 or 4 minutes left. And we've got a lot of questions that have come in. So what this is going to be, guys, is a rapid fire Q&A session. So we're going to give about a couple of seconds per question. So prepare yourself.
Coffee. Let's go.
And for everybody, that's great. For everybody on the call, yes, we will share the presentation at the end of the webinar. The first question is frequencies we support, and I can really quickly answer that. So VHF, UHF 450 to 470, we support 700 megahertz, we support 800 and 900 megahertz. So all of those frequencies are supported, and I mentioned VHF as well. So one of the questions that came in, main difference planning Mimomax networks versus LTE, and maybe Doug, a couple of seconds on the difference between Mimomax and LTE planning.
Well, obviously, with LTE these days, they take a totally different approach to the channel reuse. They don't have a channel reuse plan. That is all done dynamically by the node controllers and the further up the network. So they don't actually do frequency planning. From a coverage point of view, it's similar, although they would actually be they're wider band signals, so there are some different property characteristics of those, and John can comment on that. And they also, for any given base station, of course, they actually don't need anywhere near the same kind of availability because they rely on the adaptation of the network. If you can't get access to one base, it'll simply direct you to another base.
Okay, thanks, Doug. And another one came in around determining capacity, and I think this is in particular to backhauling land mobile radio, supporting some control data, telemetry, and perhaps NMS. So in terms of supporting capacity, John, a couple of seconds on that.
Supporting capacity, again, it very much depends on the application, and that is one of the things we need to do early on, is understand what sort of data they're trying to transport over the system, what is the the packet size, the how often the outstations or how often that has been backhauled. Point to point, we have some pretty clever capability there as far as backhauling, say PMR, with our compression ratios, with the MDAP, which sort of goes against what most of the LMR vendors, they say they might need for a P25 channel 50 kilobits per second. We can run that around 12 kilobits per second over our links. So we're very adept at designing the capacity. Also, some of that, when we assign capacity for LMR, whether it's DMR or P25, that's dynamic as well. So we also, while those channels are not being used or there's no traffic, the full IP bandwidth is available for maintenance, SCADA or whatever. Could be slow rate frame video or something like that for site monitoring.
Yeah, a key factor to add to that too is that obviously we run quality of service stuff over the link, so you can give your priority traffic, guaranteed to get through, and put background traffic on a best endeavours basis. So we support a range of priorities.
That's great. Look, we've just gone over the hour. There's a lot of questions left, but I think what we'll do is we'll endeavour to sort of answer those questions to those people that raised them, and we'll be in touch. Just like to thank everybody for joining us this morning on the Smart Radio Network Design webinar, and thank Doug and John for getting up early and charging themselves with coffee and presenting as well. Thanks, guys. I think the final words from me is that, sometimes these things are unknown up front in terms of sizing the network. You often, sprinting to do a justification. There may be a rate case or there's some ROI required. And the chicken and the egg scenario is that you're not too sure around the size of the network to be able to build the appropriate costing or justification in for the network. One of the things that we do here at Mimomax is we offer to support you in terms of sizing that up front. If that means, asking John and his team to do a preliminary coverage design there and give you a sense or a rough order of magnitude of where the network might land, then we're very happy to do that. So please keep that in mind, and please feel free to reach out to myself or the US team if you require any more information. So thank you, everybody, and have a great rest of your day.
Thank you. Take care, everybody.
Thanks.
Thank
Bye.
you.